Hi everyone. So this is going to be an introductory lesson to the idea of momentum. And I'm going to start off with it's not fair to call it a definition, but it's an explanation of what momentum is that I think gives sort of a useful feeling and an understanding in an intuitive way of how to think about momentum. So what I like to say is this: every moving object has momentum, which is a measure of how scared you should be of the object. The idea here is that objects with lots of momentum are things you should be scared of, and objects with less momentum are things that are maybe not potentially as harmful to you. So what do we need to look for in a moving object when deciding whether or not to be scared? Well, there's two things that go into this. One is the object's mass, and the other is its velocity. So let's look at a few examples. Let's start with something that has really low momentum, something that there's probably not a really good point in being scared of. And the thing I thought of was a balloon. This thing's mass is tiny, and if it's kind of floating about in the air, these things don't move very fast. Not a lot of momentum at all. Probably not worth being scared of if you see a balloon moving towards you. If you want to have something that has substantial momentum, we either need to give it a lot of mass or a lot of velocity. Trains are a good example of something that, although its velocity isn't maybe huge, you can, in a lot of cases, probably outrun a train, especially if it's going through an intersection in your town. But the mass of these things is really big. And so if you're stuck on the tracks and a train's coming towards you, there is a pretty good reason to be concerned. The momentum of these things can be really huge simply because of how massive they are. On the other end of the spectrum, we've got things that are maybe not so massive, but have a lot of velocity. The thing I thought of was a bullet. These things weigh a couple of grams, but if they're traveling, faster than the speed of sound, that velocity is so big that it actually gives the bullet quite a bit of momentum. And I think it's fair enough to say that bullet is something you should be scared of if it's moving towards you. And then I was thinking, okay, well, while we're on the topic of things with lots of momentum, what's the thing we can think of that has like the most momentum or that combines this idea of big mass with big velocity? And I came up with spacecraft. So something like this, especially once it's left Earth's atmosphere, can be traveling a lot faster than bullet and have a lot more mass than a train. So when I think of things that have, really huge amounts of momentum, spacecraft definitely come to mind. So let's take this idea of how scared you should be of something, of mass and velocity being important for momentum, and put it into a formula, a proper definition for momentum. Here we go. Okay, so this is the Greek letter rho, and that's the symbol we'll use for momentum. To find the momentum of an object, we take its mass, which is a scalar, and we multiply it by the object's velocity, which is a vector. Now, it's always important to think about units when we're introducing a new quantity. So remember that mass has units of kilograms, if we're talking metric base units, and velocity has units of meters per second. Using that information, you can probably figure out what the units of momentum are. So this equation tells us that to get momentum, we have to take mass and multiply it by velocity. So fair to say that if we want the units of momentum, we have to take the units of mass and multiply them by the units of velocity. So that would be kilograms times meters per second, which gives us kilograms times meters per second, or I can just pronounce this kilogram meters per second. Now, there is actually another way to write this unit, another unit I would accept for momentum, and that is Newton seconds. Now, it turns out that a Newton second is exactly the same as a kilogram meter per second. It's just a different way of writing it. If you want, you can try and show me how these two units actually end up being the exact same thing. And if you're curious, you can ask me and I'm happy to demonstrate it for you as well. So let's look at an example here. Start simple, just calculate the momentum of a moving object. So we have a 1,000 kilogram train and it's traveling 5 meters per second east. What is its momentum? Well, let's start with our formula. To find its momentum, I'm going to have to multiply its mass by its velocity. Its mass is 10,000. That's kilograms, so it's already metric base units, which means I can just plug it right in. And velocity, remember, because of this vector hat up here, that's my reminder that this guy is a vector. So I need to not only write down its magnitude, but also its direction. The direction I'm given for the velocity is east. However, it's tough to write east in a formula or plug it into a calculator. So I'm going to encode that direction as a plus or minus sign. And we generally say the direction east is positive. That's the convention we use. So for a velocity of 5 meters per second east, I'm going to write it as positive 5. And again, because meters per second is the metric base unit for velocity, I can just use that number directly in my formula. So if I go through and multiply these numbers, I get a momentum of 50,000, and it's positive. And then I'm going to interpret that. Remember, positive we said was east, and I should add units to this. So 50,000 kilogram meters per second east. One thing worth looking at here is what we did is we took a vector, velocity, and we multiplied it by a scalar, mass. Now this is something we'll do a few times in this course, and it's worth looking at what happened, because the vector has magnitude and direction, and then the scalar we multiplied it by had just magnitude. So what did we do? Well, we basically just took the vector's magnitude, 5 meters per second, and multiplied that by the scalar to give us 50,000, and then the direction of the vector just stayed the same. And that's a common way to think about this. When you multiply a vector by a scalar, you multiply its magnitude, and its direction stays the same. Next question is, okay, so now we have a sense of how much momentum this train has, how scared we should be of it. How fast would a smart car need to go in order to have this same momentum, in order to be this same amount scary, if you will? So now we know the momentum we want to have, and we got to figure out the velocity. In other words, we want to isolate v in this formula. So that gives me momentum over mass equals velocity. My momentum was 50,000 kilogram meters per second east. And my mass of this smart car is 730. And that should give me about 68.5 meters per second. And that'll be a positive number, so that means this velocity would be going to the east. But since the question didn't actually ask me for the full velocity, it just asked me how fast, I can leave the answer like this without the direction in it. It's really just asking me for the speed here. Now, there's a lot of quantities in physics where simply knowing the quantity itself is not that exciting or not that useful as an end game. What really becomes powerful is when we look at how the quantity changes. Energy is one of these quantities. Just knowing the energy of an object on a cliff, not hugely useful, but watching how the energy of that object changes as different things happen to it is a really powerful idea. Momentum is a lot like this. Many times we'll be more interested in the change in momentum than in the actual momentum itself. So if we want to calculate change in momentum, let's think what symbol we'd use for that. The symbol would be delta rho. Where delta means change in, and then rho is momentum. Change in momentum. Now, remember that to find the change in anything, we have to look at final minus initial. So change in momentum is momentum final minus momentum initial. So momentum isn't the only thing that follows this rule. Change in velocity is velocity final minus velocity initial. Change in energy is energy final minus energy initial. Change in anything is just final minus initial. So in this particular question, we're asked to find the delta rho, the change in momentum of a bouncy ball that's hit a wall and then bounced back. It's going east to start off with, and then it bounces back going west. I'm going to draw a little diagram here just to help me kind of wrap my head around this. So here's my wall. And here's my bouncy ball. And it is traveling at 32 meters per second east. We'll draw east as being to the right. Now it hits the wall, and then a little bit later, it is now bouncing back in the opposite direction, west, at 20 meters per second. So I'll draw the ball again a little while later down here, only now it's traveling west, not quite as fast as it came into the wall at, 20 meters per second. So in order to find the change in momentum, I need to know the final momentum and the initial. So why don't we calculate each of those on their own, and then we can plug them back into this formula. Momentum final is going to be mass times velocity final. Now the mass we have here is 30 grams. Now grams is not a metric base unit. So we don't want to put a number of grams directly into our formula. We're going to have to convert it to kilograms first. And that would be 0.03 kilograms. And then the final velocity of the ball at the end of this event is my 20 meters per second to the west, or negative 20. So if we go and calculate that, 0.03 times negative 20, we get negative 0.6. And units will be kilogram meters per second, but we're not done the problem yet, so I'm not going to worry about the units at this point. The initial momentum is going to be mass times initial velocity. Again, we're talking about the same ball, so it'll have the same mass. And the initial velocity is this guy up here, 32 meters per second, and it's going to the east. So positive for east, 32. And then if I go and multiply those guys together, I get 0.03 times 32. I get positive 0.96. So now that I have my final momentum and my initial momentum, I can plug them back in over here. Now signs are important here. So my final momentum was negative 0.6. That negative is key. And then I'm subtracting my initial momentum, which was positive 0.96. So keeping track of what's positive and what's negative is really important here. If you get that wrong, you're not just going to get the sign of your answer wrong. You'll get the magnitude wrong as well. So plugging this in on my calculator, I should get negative 1.56. So my change in momentum, my delta rho, is negative 1.56, or 1.56 kilogram meters per second west. So there you go. There's an initial look at momentum. A few concepts that we went over here that I want to highlight again. One is this idea that if you want to know the units of something in a formula, you can plug units in. So we plugged in units for mass and we plugged in units for velocity. We multiplied them and that gave us the units for momentum. Another key idea was to always remember direction when you're dealing with a vector. If I'm subbing something in for velocity, because velocity is a vector, I need to pay attention to whether that number is positive or negative. That is really important. We also learned that when you're multiplying a vector by a scalar, you basically multiply their magnitudes together, and then the direction stays the same. There's also this idea that's really important that the change in anything is final minus initial. And that's it. Those are the key ideas for this lesson. And I think if you've got a good grasp of those, they'll serve you well going forward.